Let's talk first about the shared address space model. In this model, a process is a virtual address space, but it's not just an address space because an address space is a static entity, whereas a process is a dynamic feature. So it's a virtual address space plus one or more threads of control. And that means that that a process could have a single thread of control in which we have a kind of a heavyweight process model. Each process has its own address space, but it could have multiple threads of control when we have a thread-based model, and that means that there are different parts of the process in execution by different processors at the same time. But they all share this address space, at least they all share most of this address space. Now, a process's multiple processes or multiple threads don't share the whole address space. In fact, what they will share is a portion of the address space as shown in the diagram below, along with a private portion of the address space. And what's in the private portion of the address space is what? Well, think about it. First of all, it'd have to be the process stack, and also not just the stack, but it would have to be private data that can't be shared among the threads. If we have a thread-based model, processes are normally going to share almost all of their address space except for the stack. But if we have a heavyweight process model, processes might share a portion of their address space, but the majority of their address space would be private to the process. So that's the difference between processes and threads. In any case, since we do have shared memory, we can use reads and writes for communication. In other words, one process or one thread can read a shared variable after another process or thread has written that same shared variable. And then we do have to synchronize because we can't deal with concurrent access to the same variable. We can't have two processes that are trying to increment the same value at the same time, let's say. So we have to lock one of them out while the other one operates, and that requires an atomic operation that's used for synchronization. Now, let's talk a little bit about how processors that use this kind of communication tend to be structured. One way is via a crossbar switch. And notice here that we have all the processors on the left-hand side of this diagram and all the memories on the bottom. And not only that, but we have I/O controllers that have to access the memories as well. So all of these various devices that are accessing the memories have a direct connection to all of the different memories. The nice thing about that is that as we add more processors, we add more connection points, so bandwidth scales with the number of processors. But bandwidth isn't the only thing that scales. Cost also scales, but it scales not with the number of processors, but note that you need a connection from each processor to each memory. So every time you add a new processor, you've got to add a connection to every memory, and that means that cost scales with the square of the number of processors. This is sometimes called the mainframe approach because back in the days of mainframes, you had all processors that were communicating with all memories, and the switches were robust enough that they were allowed to do that. The problem is that as we've gotten up to more and more processors, it's just become infeasible. Now, if you have 4 processors, it's possible that you can use a crossbar switch to communicate with memory. But when you have more than 16 processors, the cost of the crossbar switch is too important a component of the cost of the system. So you're spending too much on the switch and not enough on the rest of the system. And also you've got a lot of logic in the switch which takes up room. So it really is not cost effective to build big crossbar switches. So the other thing that you could do is just put all processors and all memories on the bus. And that's pretty simple. It's called a symmetric multiprocessor because all processors have the same priority of access. But the advantages and disadvantages are the reverse of what they were with a crossbar switch. The advantages are all in cost, and the disadvantages are all in performance. The latency will be larger than for a uniprocessor because any memory reference needs to transit the bus, and in order to get to the bus, it's got to arbitrate for the bus. But of course, you can add devices by simply attaching them to the bus. You don't have to expand the switch the way you did with a crossbar switch. And then the bus becomes a bandwidth bottleneck as you add more and more devices. Because not only do you have arbitration, but you have contention on the bus where somebody wants the bus, they've got to keep trying for it until they get it. And that imposes potentially a very large overhead on memory references. So a compromise between these organizations is normally used. I say normally used. If you have, let's say, up to a couple dozen processors, you might use a bus. But beyond that, you have to use some other kind of interconnection network. And normally, it's some kind of multi-stage interconnection network where you've got the processors on one side and the memories on another side, and any transfer that has to occur from processors to memory needs to transit the switch, and it transits the multiple levels of the switch. So the advantage of this is that you can do communication from processors to memories without a lot of contention, but of course you do have a little bit of contention, and thereby that's why it's called a compromise between the other two. It allows more parallel transactions than a shared bus, but unlike in a crossbar, there's still a chance of communication between two transactions. Let's assume that in this case, processor 0 is trying to reference memory 0, while processor 1 is trying to reference memory 4. The path from processor 0 to memory 0 is to go straight across all of these switches. So these switches need to be set to pass through their inputs to the corresponding output. But if processor 1 is trying to communicate to processor 4, well, that message needs to go from processor 1 across this link of the bus and across that link of the bus, and then cross over here and go down to memory 4. But that means that these two switches need to be set differently. They need to be set to pass through to do the 0 to 0 connection, and they need to be set to cross over, this one and this one, to do the 1 to 4 connection. So you can't set the switches in two ways at the same time, and one of the transactions will have to wait. So that's why you say we can get a lot of transactions through at the same time, but you can't process arbitrary sets of transactions like you can with a crossbar switch. And so this is cheaper than a crossbar switch, but it's also not quite as fast. So that's what we have to say about a shared memory organization. And now we'll go on to message passing.